Now we're going to work on energy mechanics part 2. So again, we're going to start with the kinetic energy formula. Familiar, 1/2 mv squared. We're going to take the derivative with respect to position, pointing out dv dx. We're going to use that trick again, where we look at the rate of change with respect to time, and then time with respect to position. So we just break this into two parts. And again, these would, mathematically, you would say they divide out to 1. So you're just looking at it in two parts. There's nothing really magical about it. It's just, this gives us acceleration, which is really nice. So we keep on doing this. Oh, dt over dx is 1 over v. Your v's cancel. Mass times acceleration. Where have I seen you before? That's going to be a clue. They're going to be related later. Let's look at this. So we've got a block on a ramp, blocks A and B, aptly named. I'm going to start with an expression for the energy. So I just wrote kinetic energy over here and potential energy over here, block A and B. Now I want to look for connections, and the trick in this problem is this rope. So if block B goes this way, block A goes up. If block B loses potential energy, so if UB goes down, then UA goes up due to gravity. They're also attached by a rope. What else do I know about this? I know that if block A moves, block B is going to move. The trick is to always link these quantities together. Fewer variables, and you can start combining terms. They're attached by a rope. Their velocities are the same. Oh, we combine those velocities. Great. One less thing we have to worry about. Is there anything else we can combine? Well, we can relate the positions. I know that block B goes up and down. I know block A is going either this way. So that's the S direction. So can I relate block A's Y position in terms of S? I bet I can. So what I will do is I will put them together. All right, so Y of B links with the sine of A. This is the direction it's moving. This sign accounts for that potential energy from gravity only matters when you go up and down. All right. And then, oh wait, we're getting here. How did I do that? Well, I took the derivative. And this is that other trick where you go, this is 2v dv over dt dt dx. And then this is 1 over velocity. Let's use a different color. That goes away. That cancels with this. This 2 cancels with that 2. And that is your acceleration. It's a little messy, but it worked. The second thing to know is that if block B goes down, block A goes up the ramp. So if block B loses potential energy, block A gains potential energy. It's this negative relationship. So that comes into play when we take the derivative with respect to position right here. All right? So that was that relationship. Now the problem's set up. I've linked as many quantities as I can. What do I do with them? And the answer is you plug it in, you get this nice expression, and we can solve for the acceleration of this system, which we do. Now, if this is an isolated system, so if this is isolated, that means delta E is equal to 0. Delta E is equal to 0, that means, well, delta E with respect to anything is 0, so you don't have to worry about that. If you had friction, it would pop up in that term. All right, and we now have a wonderful expression for the acceleration of a system. Now let's see, do you see any variables in here? Other than, like, mass. Nothing time-dependent, nothing position-dependent. This is constant. Which means, if it's constant, you can just use your kinematic equations. So we've ran a problem, we've seen how we can get our kinematic equations. Let's look at if energy changes with respect to time. This idea is called power. Its unit is the W, or watts. It's in watts. All right, so we'll look at this block. It's going up a 30-degree ramp. Write your expression for energy. Let's look how it changes with time. Same thing we did before, relating our Y positions with the distance up the ramp, this S-axis. This is just so we can relate how far it moves with Y position. dE dt, apply the definition of power. And, oh wait, dV dt, that's an A, plus mg ds dt. Well, ds dt is just V. All right? And you will get a wonderful expression for the power that this system is exerting. Power is rate of energy transfer. So this is how much energy is going in or out of the system every second. If you combine with your kinematics equation, because we knew that it was a constant, we plug it in. You use your constant acceleration kinematic equation, just like we've always done. Get your numbers in there, and you get your acceleration. Pretty nifty. Keep on plugging this back, and 10.2 watts. Let's talk a little bit about a basic problem-solving strategy. It's energy-based physics, so naturally, we're going to start with the energy of the system. You define it. Then, I want you to combine as many terms as possible. Fewer variables, easier it is to work with. Also, the more quantities that are interrelated helps you visualize the system. Differentiate with respect to position to determine acceleration. A lot of the times, differentiating with respect to position is actually the easiest option. If you have forces or friction or some other way that's adding energy to the system or taking energy away, you set that derivative equal to this rate. If it's an isolated system, it's just 0, and that's fine. And then if A is constant, back to your kinematic equations. Otherwise, you've got to integrate. But this will work for another. It's just another way of going about it using the energy-related approach to this. I hope this helps, and I will see you in class.